Hello everyone, welcome to this channel. And today we are going to talk about a physics question about projectile. I know that it is a common question in A level, but this question is a bit different. Usually in A level, you're required to find the maximum horizontal distance, but today we're actually going to find the angle such that it is always moving away. So when I say it is moving away, I'm actually talking about the distance from the launch point to any point on the trajectory, which is the parabola here. So we know that horizontally we have the displacement xt, and vertically we have yt, and then this displacement here, we call that rt. So we know that r equals to square root of x squared plus y squared, and that's Pythagoras, pretty easy. So we want that to move away from the launch point, and we want to find the angles such that it will be always moving away. And as an A-level student, I guess the easiest way or the most straightforward method will be to take derivative. So dr by d theta. And we want that to be moving away, so that we want that to increase all the time. So we'll put that in that equality. But I'd like to explain an easier method to solve this kind of question. So before moving further down into this question, I'd like to talk about two projectiles that are fired at two different angles. One is 60 degrees above the horizontal and one is 75 degrees above the horizontal. And we can see that they have quite different motions. And the graph beneath them are the distance from the launch point. You can see that the red is always increasing while the blue seems to increase at the beginning and then is having a stationary point and downturn. Later on, it is increasing up again. Now, the question I'm going to ask here is whether there is a relation between the angle and whether the displacement is getting larger all the time. So we have a particle doing circular motion here, and we know that the acceleration is always perpendicular to its velocity, so that the magnitude of its velocity stays the same. And we know that acceleration is the derivative of velocity. So now we know that the velocity is perpendicular to its displacement from the very center, like here. And we know that the velocity is actually the derivative of its displacement. So if we apply the same math here, we can know that when the displacement is perpendicular to the velocity, the radius or the displacement should not change all the time. And now I'm going to show you why when the angle is smaller than 90 degrees, it is moving away. So imagine that this is the displacement and this is the velocity. We can resolve the velocity in two directions. One is the same as the displacement, which is called v1, and then one perpendicular to that, which is v2. So we can see that v2 is not going to change the size of the displacement as it is perpendicular to it. And v1 is pointing in the same direction, so it is actually causing the displacement to be greater. And we can draw that in a different way, so that it is making an obtuse angle. And if we resolve that in two directions, one is the opposite direction of the displacement, and one is the perpendicular direction of it. We can see that this component, v2, is not going to change the size of the, and this is actually causing the to be smaller. A good illustration of this will be planetary motion. So when the planet is orbiting the Sun in a circular orbit, we know that its displacement will not change. And when it is doing an elliptical motion, we can see that while it is moving away from the Sun, its angle is smaller than 90 degrees. And while it is approaching the Sun, its angle will be greater than 90 degrees. So now let's focus on the math. We know that we have an angle between the displacement and the velocity. And we know that we want the angle to be smaller than 90 degrees so that it is always moving away. And one good way to make sure that is to use dot product, because we know that dot product will be equal to the product of magnitude times cos the angle. Since angle is smaller than 90 degrees, we know that cos is greater than 0. So then we can say that d dot v is greater than 0. So now let's write down the displacement of the projectile. We know that there are two directions, horizontal and vertical. Horizontally, the motion will just be a linear motion in constant speed. So that's going to be vt cos theta. And vertically, it's going to be linear motion with constant acceleration. So that's going to be vt sine theta minus half gt squared. Then the velocity is going to be the time derivative of the displacement. So that's going to be v cos theta and v sine theta minus gt. And if we times them together, that's going to give vt cos square theta plus v square t sine theta. Sorry, I dropped the square here. Then minus vgt square sine theta minus half vgt square sine theta, and then plus half g square t cubed. And we want that to be greater than 0. And we know that when the motion happens, time is always greater than 0. So we can cancel times on both sides. So by trigonometry, we know that cos squared plus sine squared is equal to 1. So the first two terms can be combined as v squared. And then secondly, we know that the third term and the fourth term have the same factors, which is vgt sine theta. So that we can just combine the coefficient, and that's going to be 3 over 2 vgt sine theta. For the last term, it is left alone, so we just write plus g squared t squared, and we want that to be greater than 0. So now we have two variables. One is t, time, and one is theta. And we know that we want to find the angle such that it is always moving away. So then that means no matter what value t has, the inequality should hold. So this inequality may seem a bit complicated because you got two variables here. However, it may actually be easier than you expect, because if we look at the variable t here, it's going to be a quadratic form. So let's say if we look at this inequality as an quadratic equation of time, and we want that to be greater than 0 all the time. So that means that if we plot the graph of ft over t here, it is not going to have any intersection with the horizontal axis, which means that it's not going to have a solution. So in that case, we know that the discriminant is going to be smaller than 0, and discriminant equals to b squared minus 4ac. B squared is just 9 over 4 v squared g squared sine squared theta, and minus 4ac minus 4 times a, which is half g squared, c, which is v squared, and we want that to be smaller than 0. So if we move the second term to the right, that's going to give 9 over 4 v squared g squared sine squared theta smaller than 2g squared v squared. And we know that g squared v squared are just two numbers, and they're definitely greater than 0, so they can be cancelled. And if we move the coefficient to the right, that's going to leave sine squared theta smaller than 8 over 9. And we know that sine theta is going to be greater than 0 because theta is an acute angle. So sine theta is going to be smaller than 2 root 2 over 3. By doing the inverse angle of sine, we know that theta is going to be smaller than 70.5 degrees. So here we have a projectile that's fired at 70.5 degrees, and we have a graph that shows the distance from the launch point. You can see that the graph keeps increasing all the time even though there's an inflection in the middle,